Hey everyone, welcome back to my YouTube channel Summarize AI. This video will be highly informative and valuable for AI enthusiasts. You will learn how vector embeddings enable semantic search and help deliver accurate, context-aware results. We will also explore LLMs, fine-tuning, RAG, and vector database. But on the first place, why we need RAG if we are already having fine-tuning? Even though fine-tuning is powerful, it can't replace RAG. Looks quite confusing. Let's try to understand same in detail. AI models are trained on websites, blogs, code repositories, and other diverse sources, making them generalized models because they learn from broad general purpose data. For example, ChatGPT 4 got trained on mix of internet text, books, Wikipedia, and code, whereas CodeLlama or Codex as an LLM model got trained on open source repositories like GitHub and programming tutorials. We call it pre-trained because the model is first trained on large general purpose datasets before it's used for specific tasks. This initial training gives it a broad understanding of language, code, and reasoning, so it already knows a lot. Later, it can fine tune or adapt it to a particular domain without starting from scratch. Fine tuning is the process to add the AI your custom data, writing style, tone, and patterns, but it doesn't keep the model updated with new information. Once you fine tune a model, its knowledge becomes frozen, and any new updates in your blog, product, or policies won't be learned unless you retrain it again. Fine tuning AI models requires significant effort, cost, and resources even for making a small update or change. For example, if you ask an AI model, what's today's weather in New York? Fine tuning won't help because the model only knows information up to the point it was trained. Its knowledge is frozen and cannot reflect the real time data like current weather, stock prices, or breaking news. Here, RAG solves this issue by letting the AI pull fresh information directly from your database or documents in real time. Instead of remembering everything inside the model, RAG gives the AI the ability to look things up whenever needed. That means your answers stay accurate, current, and aligned with your latest content without retraining the model every time something changes. Now, let's try to understand how this RAG works. Imagine you have a large data in the form of data or documents. The first step when we go for a RAG is to break these documents into smaller chunks, making them easier for the AI to process and analyze. Next, for each chunk, the system creates a vector embedding, a numerical representation that captures the meaning of the text rather than just a word. Think of a vector embedding as a list of numbers that represents your text. Every AI model produce very big list of numbers. Here we are using OpenAI's text embedding 3 small embedding model, which by default creates a list with 1536 numbers. And because different embedding models produce vectors of fixed sizes, for example, OpenAI's text embedding 3 large embedding model creates 3072 vector embeddings. Here, embeddings are 1536 in number as the dimension length of the embedding vector you will store in the embedding column. Now let's talk about more on embeddings. There are two types of embeddings. The first one is the static embedding, and the second one is contextual embedding. Imagine a vector space for static embedding. You can imagine it as a multi-dimensional graph having 1536 dimensions. But we will simplify it to 2D or 3D for illustration. Each word or sentence is represented as a point in this space based on its meaning. Here, the word apple always mapped to the same vector, no matter if you're talking about fruit or the company for the revenue. The major disadvantage here is the model cannot distinguish context, as a query for Apple revenue may incorrectly retrieve information about the fruit. In case of contextual embeddings, even though the word Apple is the same, the context changes its meaning. The embedding captures these differences. Here, instance between vectors indicate semantic similarity. Apple as a fruit is closer to banana or orange, and Apple as a tech company is closer to Microsoft or Google. Here it is having that context. Now, these embeddings are then stored in a vector database, a specialized type of database designed for fast similarity searches. Either your sentence is small or large, the embedding size never changes. Here, as you can see, we have multiple sentences, and for each sentence, regardless of its length, a vector embedding of length 1536 will be created. This is our Postgre vector database. And as you can see, there is an entry for every sentence or row, and each vector embedding has 1536 dimensions or length. Since we are using the vector embedding 3 small model, and if we are going to use any other model as a large, then the number will be different as 3072, and these vector embedding number depend on the LLM model. So now if you see these number, these are going to be 1536 here. Okay, and as mentioned earlier, if the sentence is one word or multiple words, the embedding is going to be always 1536 in number. So this length or the count is fixed. Imagine you are describing a fruit. If you only use one vector embedding as taste, your description is weak. Now, if you use five vector embeddings as taste, smell, color, shape, and touch, your description is better. Your context will be better. But if you have 1536 embeddings, your description is going to be extremely detailed. And vector length in number is nothing but the number of vector embeddings. Okay. Now, on what basis do we decide the vector length? We do not decide the vector length. First of all, we just choose the vector length, and the AI model decides it by default or out of the box for you. Now that our data is stored in the vector database, we can continue adding more information to our database to enhance our retrieval capabilities, and we are ready to start querying it. Now, when we provide a search query, this search query also gets converted into a vector embedding. Now, these vector embeddings get compared with the embeddings of stored documents to retrieve the most relevant information based on semantic similarity rather than just matching keywords. Thank you so much for watching this video. If you liked this video, please give it a thumbs up, share it, and subscribe to support my hard work and stay updated with more content like this.